for some problems, we can make an approximation that makes the calculation much, much easier and doesn't affect the answer much at all. So, if the equilibrium constant K is small, that means the reaction does not proceed very far towards the products, which means that X, the amount of change, is going to be a small number. If the initial reactant concentration is relatively large, we can assume that X is so small that it doesn't really matter, and the reactant concentration is essentially unchanged. Now, this bothers a lot of students, and I understand why. Because how can you have something and subtract a little bit and still have the same amount, right? So I live in Reedley, where we have lots of semi-trucks full of fruit. Sometimes nuts, occasionally vegetables. There's some public scales, and so you'll see a big truck loaded with oranges pull up to get weighed on the scale, because they need to know the mass of the oranges in the truck, right? So they have a weight of the truck, and they subtract that from the weight of the whole thing, and they write it down, and it's going to be tons. I don't even know how many tons, but lots of tons. Suppose, as they're pulling out, an orange falls off the truck. This happens. Usually it's not just one orange, it's the truck went around the roundabout a little too fast and spilled like a whole bunch of oranges. And then everybody has to drive through them, and it gets very sticky. Yeah. Reedley's a special place. That's another question. Would losing one orange mean that the truck driver has to go back and weigh his load again? No. Because how precisely do you think that load was weighed? To the nearest ounce? I doubt it. Probably fractions of a ton, which is 2,000 pounds. So you take that off, does it actually matter at all? No, it doesn't. So here, what we're saying is that X is so small, it's like the orange falling off the truck. It doesn't matter. So we can do the calculation as if it was 0. We do always have to check this, though. So we check it by comparing the value of X that we calculate using this assumption to the number it was subtracted from. And it needs to be 5% or less. So if X is like 10% of what it's being subtracted from, that's going to cause an error. But if it's 0.1%, it's not going to matter. Okay, so let's see how this would work. This is known as the X is small approximation. Very catchy title. So A is in equilibrium with B. Here's our equilibrium constant. This is a small number. Initial concentrations are 1 molar for A. 1 molar is actually a relatively high concentration. And B is 0 molar. What are the equilibrium concentrations? So we need an ice table. Here's our ice table. Initial 1.0, initial 0.0. This one's going to go down by some number x. This one's going to go up by 2x because there's a coefficient of 2 here. So at equilibrium, we add initial and change. This is a review of Tuesday. And we get 1 minus x, and over here we get 2x. And so what we're going to do then is we're going to write the equilibrium constant expression, b squared over a. And we're going to plug these things in. So there's K. And K is equal to b squared, where b is 2x, divided by a, 1.0 minus x. It's the Raspberry, and I don't know why it does that. During one of my lectures every week.
It just wants to. It has stuff to add.
It does. So, anybody have questions about that? Now, what we did on Tuesday is we got out our solvers and we plugged this in. We're learning the X is small approximation today. So this is a small equilibrium constant. It's not going to form a lot of product, which means that X is small. So we're going to suppose that X is so small relative to 1 that it doesn't really matter. X is small. So this X, we're saying, is basically 0. It's so small it doesn't matter. Can we make this X 0 also? No, because then this would be 0, and 0 does not equal 3.3 times 10 to the minus 5. It just doesn't. So we only make the x's that are added or subtracted to numbers 0. The x's that are just here and being multiplied, we leave alone. And this is kind of a reach, but there's a kid coming home from school and they're hungry and they find this orange on the sidewalk. Is that nothing to them? No, it's not. They're hungry. It's like, oh, cool, orange, I'm going to eat that, right? So here's the X. It's not relative to anything. It's not being added or subtracted, right? It's just by itself. So we leave those X's. So there's 2 ways you can remember that.
Okay.
Yeah.
Do you have an extra 3 there for?
I did that to see if you were paying attention. That is an extra 3. You are correct. Thank you. Let's see if I can get rid of it easily. Ooh, there we go. Thank you. Yeah, we don't want extra 3s hanging around. Okay, so now this side is the quantity 2x squared over 1, right? So we could simplify that. So that's going to be 4x squared divided by 1. Doesn't change anything. So we got this side, divide by 4 is equal to x squared. Take the square root of both sides. Yeah. X equals 0.00287. Now, if you and algebra don't get along very well, you can still use your solver. That's fine. You can even just, do the approximation and then just say, well, I'm going to plug in the quantity 2x squared equals this into the solver because I don't want to mess around. Fine. Absolutely fine. So if we think about just significant figures for a minute, we started out with 1.0 molar, which suggests that there's uncertainty in the 10th place. If we subtract 0.00287, what does the calculator tell us? It tells us 0.99713. But we're subtracting. This is the uncertain digit. We have to round, so there's only one uncertain digit. So we're going to report that as 1.0. I know that seems troublesome. How can you subtract something and have it be the same? Well, it's not actually the same, but it's so close it doesn't matter. Okay? Anybody want to talk about that? It can be disturbing. Anyway, so that's just sort of a sig fig way of looking at it. But what we really have to do is we have to check that this number is 5% or less than the number it was subtracted from. So we take our x We divide it by the number we subtracted it from. We multiply by 100 to get a percent. And we found out it's 0.287%, much less than 5. So that's the approximation. We still need to answer the question. What are the concentrations? Well, A is going to be 1 minus X, which is this little tiny number. We did that. I erased it. And we realized, well, considering sig figs, it comes out the same. And then what about B? Well, B is 2 times X. .00574. And that would probably be best expressed as 0.006 molar. Any questions? Yeah.
So we would apply this, excuse me, we'd apply this if the K is small, so
Mhm.
how small are we considering?
That's a good question. You kind of eyeball it, and then you always have to check. Always have to check. Yeah. We'll do an example where it doesn't work. Any other questions? Okay. Let's try a more real-world type problem. So here we've got hydrogen disulfide decomposing into hydrogen gas and sulfur gas. Equilibrium constant 1.6 times 10 to the minus 7. That's pretty small. Reaction mixture contains 0.1 molar H2S and 0.1 molar H2 and no S2. And they're asking us to find the equilibrium concentration of S2. They threw 800 degrees Celsius in there. We don't need to worry about that. This is the correct rate constant at that temperature. We are dealing with a reaction at that temperature. So we don't need to worry about that. So we need an ice table. So we've got the H2S, we've got the H2, with the S2. First row is I, second row is C, third row is E. Initial change, equilibrium. Write in the initial concentrations. These are given. 0.1 molar. And hydrogen is also 0.1 molar. And sulfur is 0. So next we put in the changes in terms of X. Probably a good idea that if you have one that's 0, start with that one. Can we subtract from 0 and get a reasonable concentration? No, we can't. So this one must be going up. It has to go up. It can't go down because it's already at nothing. So if this one's going up, this one is on the same side of the arrow, it also has to be going up. And is it going up by 1x? 2x. And that's the coefficient here. So the product side was plus, then the reactant side has to be minus x, and again we have a coefficient of 2, minus 2x. So then we put these together. We write our equilibrium constant expression, H2 squared times S2 over H2S. squared. And then we've got numbers and expressions that we can plug in there. So 1.67 times 10 to the minus 7. That's the equilibrium constant. H2 at equilibrium is 0.100 plus 2x, the quantity squared. S is just x. And down below we have H2S, which is this guy over here. 0.11100 minus 2x, the quantity squared. Any questions? We could do this on a solver. That's always an option. Or we can say, well, this k is pretty small, 10 to the minus 7. 0.1, I mean, that's not as big as 1, but it's not like 0.00000000005. So let's try it. So the x is small says that x is so small that even though we're multiplying it by 2 and adding it to this, it doesn't really change anything. So in this example, 2 oranges got put on the truck or 2 oranges got taken off the truck. It still just doesn't matter. So that means that this is 0 and this is 0. Right? And then what's left over here? 0.1 squared times x divided by 0.1 squared. Well, those 0.1s are going to cancel out the 0.1 squared. So the result is that x is equal to the equilibrium constant. Then we have to check, do the test. So we take x, the x that we calculated, we divide it by the number that it was added to or subtracted from. We multiply by 100. Well, that one's really tiny. And I even left out one of the zeros. See, that nap helped because I caught my own mistake that time. So we used the x is small approximation. We tested it and saw that that was correct. What's the answer to this problem? This time the answer is x. They're asking us for the concentration of S2, which is equal to x, which is k. Okay. So this is our answer. But sometimes, you know, if they had asked us, well, what's the concentration of H2 at equilibrium, then we have to do something, right? So x is not always the answer. Any questions? Yeah.
I'm just kind of curious, what is the, not noticing the full importance of this, because isn't that just equal to KC? Like, what is putting it to 0 actually do?
Okay, so why do we put this to 0?
This kind of confused on why we're just solving for KC, like what we've been doing this whole time, because it's different.
Well, so solving this equation, currently not a big deal. When I was in college, big hairy mess, right? Because you're going to have to do the squaring and distribute things and rearrange everything so you get a nice polynomial, and then use the quadratic equation to find out what x is. Nobody liked doing that. Nobody. So, do we have to use this approximation? Absolutely not. You do not have to use it. But especially if math is not your friend, this might be a good thing to do, right? So I'm just going to tell you, on homework problems, lab problems, there may be things where you have to use the solver or the quadratic equation to find out what x is. On exam problems, we won't do that. So you should still check, but unless there's some mistake, x will always be small on the exam questions. Yeah. Any other questions? Okay, let's do this one. Kind of looks like the same problem, because it's almost the same problem. Same KC, same equation, but now our initial concentration is 1 times 10 to the minus 4, a lot smaller, right? And we've got no product. And again, they want the equilibrium concentration of S2. I thought of this too late. I could have copied my ice table and just changed the numbers. ICE. So initial concentration of H2S, 1.00 times 10 to the minus 10 to the minus 4. And this is 0, and this is 0. Well, look at the columns that start with 0. These have to go up. So this has to be plus x. There's a coefficient of 2, so it's plus 2x. This one has to be plus x. The coefficient is 1, so it's 1x. Other side of the arrow, it's going to be negative, and this will be negative 2x because of the coefficient. And it doesn't fit there very well, but that's okay. Got our equilibrium constant expression. I could have copied that too. Maybe next time. Plug things in. 1.67 times 10 to the minus 7 is equal to, now h is 2x, the quantity squared. S is just x, and H2S is 1.00 times 10 to the minus 4 minus 2x squared. I'm not going to do the highlights, if that's okay. Oh, it's kind of a sad looking minus sign. Almost looks like an underscore. So let's try using x as small. Are these zeros on top going to be 0? No. This is the one that's going to be essentially 0. We're going to say, well, this one's so small that subtracting 2 times it from this number doesn't matter. So we'll say this is essentially 0. So what we're left with over here then is 2x the quantity squared times x divided by 1.0 times 10 to the minus 4. And that's equal to the equilibrium constant. Now, you could use algebra to solve this. If you want to, you can use the solver. Yeah.
How come the top x isn't 0?
That's a good question. Why isn't the top x 0? If we make these x's, either one of them 0, then this whole thing is 0, and 0 is not equal to this. And we can't have a true expression here. So it's only when you're adding or subtracting. It's not when you just have x by itself. So you can solve this kind of however you want. Yep. Thank you. Thank you. Yes, we need to square the bottom part. It was over here by the thing that became 0, but that doesn't mean it went away. Thank you, you saved me from utter embarrassment. Bless you. Sure I did that right. No. Cube root 1.67 times 10 to the minus 7 times 1 EE minus 4 squared divided by 4. Yeah. Anybody solve it and get that number?
I used the number solver and I got
Anyone solve it without the number solver using the x is small approximation? Pardon me? You got a different number? Using the number solver or the approximation? Okay, what'd you get? Okay, that sounds right. Times 10 to the negative 6. Yeah, but didn't sound right to me. You got the 6.1? Yeah. Yeah, I don't know what I'm doing wrong there. I did it yesterday and it worked just fine. I don't know. We're not going to worry about it. So this is the answer we get. We have to check this. So the way we check that, we've kind of run out of room, is we're going to take that I'm just going to call it 7.5 times 10 to the minus 6. We're going to divide it by the number we were subtracting it from, 1 times 10 to the minus 4, and then multiply by 100 to see what percent we get. .5%. Is that okay? That's not okay. And if you look at the answer that's printed on the slide, it says 6.78 times 10 to the minus 6. Well, it's kind of close. Yeah, not close enough. So this is greater than 5%, which means we cannot use the approximation. We need to use a solver. And, you know, there are lots of cool things available on the internet. And I'm sure there's several, probably Wolfram Alpha will do this, where you type this in and it'll solve it for you. Okay? That's not cheating. Because you have to get the equation. That's the part it can't tell you how to do. Okay, so I am going to make some space here. Got almost all of it. So x is small doesn't work. We're going to go back to that. Plug it into the solver. Don't write with the eraser. Six 6.78 times 10 to the minus 6. Again, we're looking for the S2 concentration, which happens to be equal to X, and so there's our answer. Once you kind of get a feel for it, you'd look at this and say, well, that's a small K. That starting concentration's kind of small too. It's probably not going to work. But you can always try it if you want to. Yeah. Mm-hmm. Ah, good question. So he pointed out that this number is still more than 5% of the number that X was subtracted from. And that's not a problem. It could be 50%, right? This is telling us that we're subtracting something that is 7.5%. It's too big. So if we're going to call it 0, it has to be less than 5%. It has to be smaller than that. Here, we're not saying that this is 0. We're actually going to subtract that from the initial value. We're not using the approximation. Excellent question. Yeah. Any other questions?
Does that mean that it's a small approximation doesn't work in this case because?
X is small, doesn't work here because X isn't small enough.
So then the correct answer is equilibrium.
This one. Yeah. So we can't take a shortcut. And, you know, the way the book and the text banks and stuff are set up is that questions you encounter on the exams are not going to make you use a solver. I think you should learn how to use it just because it's so useful. And because even if X is small, if you and math don't get along, the solver might help you solve the X is small approximation, right? Yes?
For that ACS,
Mm-hmm. So on the ACS final exam, they definitely will not make you do a solver type question.
oh, okay.
Yeah. Yep. Good questions. Okay, so this one's conceptual. Generic reaction, A goes to B. We're supposed to look at the values of K and the values of the initial concentrations and find out which set of values will most likely work with X is small. So we've got two different values for K, 10 to the minus 5 and 10 to the minus 2. what's going to be more favorable for x is small? Small k, right? Small k. Because the small k says the reaction doesn't go very far towards the products. And x is how much it goes. So it must be one of these. And then do we want a larger initial concentration or smaller? Larger. So it's going to be this one. Because this one might be like, you know, a kid comes along with his toy semi-truck that's got 5 oranges on it, right? And he weighs it, and then one falls off. Well, that matters. When you have 50 gazillion oranges, one doesn't matter. Okay? Any questions? So, some important notes about doing these sorts of problems. Concentrations have to be in moles per liter. It doesn't happen often in this course, but it could happen where you're given a concentration in other units and they ask you to convert, then you have to convert them, and they're not going to point that out to you. Okay? If you're doing this with pressures, the partial pressures have to be atmospheres. They could give you torr or PSI or something to be mean, right? Be sure to use the appropriate equilibrium constant. If they're giving you atmospheres and they give you Kc, you have to convert Kc to Kp using that equation we learned. That's also on the table of useful information. And one of the multiple choice answers will be the answer you get without converting Kc to Kp, right? So watch out for that. This one, I just don't even want to talk about. It's not worth talking about. You just don't. This is important. The x is small approximation doesn't mean that x is 0. It just means that x is so small compared to what we're subtracting it from that it doesn't matter. It's still, that orange that fell off, even if we disregard it, it still has some mass. It might be, 10 grams or something. But in the scope of the overall size of things, it doesn't matter. And so that's why we don't just make all the x's 0, only things that are added or subtracted. Any questions?